Hello everyone. In this video, we discuss regression in machine learning using scikit-learn. But before discussing about the scikit-learn implementation of regression models, including linear regression and polynomial regression, we are going to very quickly discuss problem formulation and some of the assumptions that we make. Also, we talk about the model training aspects of regression models, such as loss function and gradient. And also at the end of this video, we talk about several evaluation metrics that we can use to assess the performance of regression models. So let's get started with the simplest case, which is univariate linear regression. So univariate here means that the input that we have to our machine learning system is just a scalar. And this is exactly why here we are not using boldface letter. So therefore, in this case, our training data, which is a labeled data set, consists of input-output pairs, where the input is a scalar or a single number, and output is a scalar too. And because it's regression, this means that yn is actually a quantitative label. And in general, it can be a real valued number. So in this case, we have a parametric model where we assume that the predictions that we make are in the form of theta 0 plus theta 1 x. Something I want to mention about the naming of these variables. So here we have a lot of flexibility in terms of what we want to use to name these variables. Before we call this mx plus b or w1 times x plus w0. And like any other mathematical equation, we can use different names for these variables and then estimate them. So this name doesn't really change anything. And in this video, we are going to use theta 0 and theta 1, where in this context, theta 1 represents the slope and theta 0 is the y-intercept, also known as bias in machine learning. So therefore, the goal of machine learning, or I would say here, training a regression model, is to choose theta 0 and theta 1 such that the predictions that we make for each input xn is as close as possible to the known output or label. And this is exactly the idea of using empirical risk minimization that we mentioned earlier in the previous video, where we have to find a loss function that measures the difference between the prediction and the true value. And in the case of regression, the most popular option is the quadratic loss function, meaning that we find the difference between true and predicted value and raise this to the power of 2, and then we take the average across all the data points that we have. And therefore now, this is a function of theta 0 and theta 1, meaning that every configuration of these two will give us a different value of the loss function, but we are looking for the configuration that gives us the lowest possible value for this loss function, and that's the optimal solution. As we said earlier, in these cases where we only have a few parameters, we can use the derivative approach and start by finding the derivatives, or in this case, because we actually have two unknown variables or two optimization variables, better to say, we need to find partial derivatives and then set them equal to 0, right? So that's how we can solve optimization problems of this form. And when you want to find the partial derivative, and that's the notation that we're going to use of this loss function with respect to theta 0, you can assume that theta 1 is fixed, right? So it can be any number like 2, 5, 10, anything you want to consider. So theta 1 is not variable. On the other hand, when you want to find the partial derivative with respect to theta 1, you assume that theta 0 is fixed. Based on this discussion, then what we really want to do here is that you want to use the chain rule, if you're familiar with the chain rule of calculus, and call this term that here you have inside these parentheses as zn, or some variable name that you want. And then when you take the partial derivative with respect to theta 0 or theta 1, you have this term which is like z squared. And so the derivative of that is 2 times z. So that's why you can see here we have this 2, and then we have this term inside the parentheses. And if you're wondering why we get this theta 0 and theta 1x, that's because that's the value of f of xn, right? So if you find f of xn here is theta 0 plus theta 1 xn, and we have a negative sign here too. So therefore, we get negative theta 0, negative theta 1 xn. So you can definitely pause the video here and put all these pieces together. But that's sort of like, the first step. And then you have to find the partial derivative of the term you have inside this parentheses with respect to theta 0 and theta 1. And you can see that when you do this with respect to theta 0, you just get a negative 1, and that's what we have here. And when you do with respect to theta 1, you get negative xn. So that's the constant that you have right next to this variable theta 1. And you can see that here, that's what we get. We get a negative sign, which is here, and we get xn. So these are the two partial derivatives with respect to theta 0 and theta 1. And now the idea is that you have to set this equal to 0 and find values of theta 0 and theta 1 that will give you these two terms to be equal to 0. So something that here we have to pay attention to in this very simple problem of univariate linear regression, we only have two parameters. But in a real world problem, like for example, neural networks and deep learning, you may have millions or even billions of these parameters like theta 0, theta 1, up to theta 1 million, for example. So in that case, this is really not anymore feasible, and we have to find a better way of finding these partial derivatives. And that's where the idea of gradient becomes very important. So the idea of gradient is that we can extend derivatives to handle vector argument functions, meaning that when you have a function that accepts more than one variable, like the one that we just saw, where we have theta 0 and theta 1, and possibly even more variables, we can find a vector where each element is partial derivative with respect to one of these elements. So this means that if you have a function that accepts d variables, then the gradient, which we use this notation, this upside triangle that you can see here, and you can see that in this case, we have all these partial derivatives with respect to the d variables that we have, theta 0 to theta d minus 1. Which means that if you want to find a gradient for the very specific case that we have, we can put everything back together in an array. So we have this 2 over n, which is shared across these two. So we can factor this. And then you have the two summations. And remember, the difference is that one of these summations has this extra xn here. And now this is a two-dimensional vector or array. Something which is very important to understand in machine learning is that in many cases, you can actually write this gradient in terms of compact representations of your data. So what does this mean? Let's say here in this example where we have these n data points x1 to xn, so these are our inputs. Let's put them in a matrix of size n by 2, where right now each row corresponds to one sample and each column corresponds to one feature. So we have this first column where we have all ones, and we're gonna discuss that why we get that. But you can see that in the second column, you get exactly all the input features that we have for our n samples. And why do we get these extra ones here? So this becomes from looking at our model, that you can see that where we have this theta 0 plus theta 1x, you can write this actually as theta 0 times 1, and that 1 is a feature that is shared across all the samples. So it's never changing, it's a constant, but you can assume that that's one feature. So therefore, even in the case of univariate linear regression, we can actually assume that we have two features. So therefore, we have two columns. But the first column is always a constant. It's not really a variable. But the second column is the one that really depends on the input that you have, and it's definitely a variable. And then you form a vector theta, which includes two elements, theta 0 and theta 1. And then the corresponding outputs for these inputs that we have, which should be a vector of size n. So this is consistent with what we talked about earlier about scikit-learn, where we expect that the input data matrix, this x, should be of size n by the number of features, where n is the number of samples. And then y, which is the target vector, should be a one-dimensional array with n elements in it, which contains all the corresponding outputs. And here you can show that if you multiply x by theta, so this is a matrix vector multiplication, and subtracted by y, you get all the residuals that we were looking for, like this f of x1 minus y1, f of xn minus yn. And the next slide gets a little bit complex, and it is not necessarily for this lecture, but it is important to kind of like show that the gradient that we have here, this gradient that we found, can be actually written solely in terms of x, theta, and y. So you can show that if we have this x transpose, which means that now you're going to switch the rows and columns, which gives you a row of all ones and a row of all these x values, multiplied by x theta minus y, which we have here. This is the vector of our residuals. If we do this multiplication, right, then in this case, we can show that we are multiplying this first row by this column vector, which will give you the sum of all fxn minus yn from n from 1 to n. And similarly, we can do the second multiplication here, which is the second row by this column vector, which will give us this one. So you can see that here the main difference is that we have this xn for each f of xn minus yn, and n goes from 1 to n, which is the result of this multiplication or this dot product, because technically here we have two vectors. So therefore, this means that this is our gradient that we found. And the nice thing here, the interpretation of this is that even if we have a lot of data points, let's say we have like 1 million data points, the only thing that we really need is to form this data matrix X and then plug in it into this formula that we have here. And the same thing with theta. The one that we just showed, theta has only two elements because we have univariate linear regression. But you may have a theta vector, which is really, really large, meaning that you may have like thousands of elements inside this vector theta. And therefore, the nice thing is that now, in order to solve this problem, to find the optimal values of theta, you can set this equal to 0. And if you're familiar with topics in linear algebra, you can show that you can do this multiplication and then solve for theta. So if you do the multiplication, set this equal to 0, on one side, you get this x transpose x theta, and then on the other side, you get x transpose y. Now remember, x and y are given. That's what you provide to scikit-learn. And the unknown here is this theta. And therefore, now the only thing you really need to do is to solve this system of linear equations. So you can see that that's why linear regression is very popular and simple, because at the end, we have a very nice analytical way of solving this problem. Okay, so now let's see how we can actually implement this, even before using scikit-learn. So we're going to start with importing NumPy, pandas, matplotlib. You can see that now why we are using all these data science libraries in Python. And also we have a data set, which is called life satisfaction, which is a CSV file. And we're going to import and read this data and look at the first few rows. So this may take a little bit of time because you actually have to find these on this website and then read this CSV file. And you see that this is very familiar, right? This is the data set that we've been using before, where we have countries, GDP, and then life satisfaction, where the goal was to find a connection between GDP and life satisfaction. So let's pre-process this data and make it ready for our analysis. So we're going to look at the GDP column, and that's our input to the system, right? So you want to create a machine learning system where the input to this machine learning system is this GDP information, right? So that's our X. And then the output here is this life satisfaction, which is Y. And we want to see if we find a model that now, if we provide a new GDP, we can predict the corresponding life satisfaction score. So in this case, we're going to look at this column of the data frame, convert this to a NumPy array, and similarly for Y. So you can here always print the shape to make sure that you have the same number of data points. You can see that here that's the case. You have 27 samples. And then if you want to implement this from scratch, remember we have this column of all ones here. So we have to add that manually. So in this case, we write a function to add this column of all ones, and we can do this using numpy.concatenate that we have used before. So you're gonna create a array of all ones, and also you're gonna reshape this matrix X that we have to make it a 2D array where we have n rows and 1 column. And then we concatenate them across axis 1, which means that we want to concatenate them and put them next to each other. So we have a, again, just to show this means that we have this vector of all ones that we created. And then we have this vector of all these x values. So this includes x1 through xn. And now if we concatenate them, we get this n by 2 array, where n is the number of samples and 2 is the number of columns, right? That's why we use axis equals 1 here, because this is the direction of axis equals 1. Okay, so now if we run this and look at the shape of the concatenated array, you can see that now this is 27 by 2. And you can obviously even look at some of the rows of this matrix to make sure that that's exactly what you're looking for. And we can see that that's the case, right? So we have this column of all ones. Here I'm looking at the first 5 rows, and you can see that this second column is the one that get different values, right, corresponding to different inputs. So now that we have done this, we have to implement what we have here. So we have x transpose x, which we call it A, and then x transpose y, which is B, and then find an appropriate way of solving this equation in Python. So in this case, we form A, we form B, and in order to find theta from NumPy linear algebra module, you can find this class, which you can use for solving least squares problem, which you provide A and B. You can also provide some additional information to deal with some of these singular values of this, this matrix that we have here, this A. But again, that's something that is beyond the scope of this course, and it's kind of like optional here. But you can see that if we solve these least square problems, that's what this stands for, you can see that we get this information where it tells us this theta, which is now a vector with 2 elements. Theta 0 is 3.7, and then theta 1 is this 6.7 times 10 to the negative 5. So if you're wondering why this is really, really small, is because if you look at the column that corresponds to these features that this number will be multiplied to, you can see these numbers are really large, like they're like 10 to the 4. And therefore, this value here should be very small, right? So that when you multiply them together, overall, it gives you something that is in the range of these y values. You can see that these y values are like, in the range of like, 5, 6. I believe based on what we did before, the maximum value is close to 7, right? So obviously, if you don't have a very small theta one, when you multiply by this very large number, there's no way you can get anything close to here. So that's why you get this very small theta one here. And once you solve this problem by finding this theta, now, if you remember, we said that in order to make predictions here, actually, one thing that you can do is to multiply this x and theta, and that will give you all these f of xn to f of x1 to f of xn, right? So you just need to multiply the metrics that you have for your data by this data that you just found. And if you do that here, right, so we create some test data points that the variables that we have here for the GDP are from 25,000 to 60,000. We also add the column that the column of all ones because you have to do the exact same pre-processing. And then we can feed it into this function that we have here. And you can see that that's the regression line or the line of the best fit that we have for this problem. And these, blue ones here are our training data points that we have. So overall, you can see that this is a really good model. And remember that here I'm using some of the customization in Matplotlib to create a figure that is easy to read, increasing font size, figure size. These things are very helpful, and also adding legend to show you that this red dotted line is our prediction line. So now with this example that we just work on, now we can talk about linear models for regression in a general case. And by general case means that in this case, this xn, which is the input, can be more than just one variable, right? So before we just had GDP information, now we can have tons of more variables, right? We can have, for example, like lifestyle factors. We can have like, education factors, etc. Right? That's definitely a much better model than just looking at GDP and life satisfaction. And therefore, in this case, we can just extend the model that we have, that, this is what we just had before, but now we have more variables, and for each variable or feature, we add a corresponding coefficient that we have to learn. And you can see that, again, this can be written as a dot product or inner product. And as we said, we can assume that this theta 0 is multiplied by 1, which means that in this case, our data set that in terms of features, now we have d plus 1 features, which starts from x0 to xt. And therefore, we have d plus 1 parameters that we have to find. And the prediction model, the way it works is that you find the dot product or inner product between theta and x, which is this weighted sum, and that's our prediction. So this is the generalization of y equals mx plus b that you have seen in 2D spaces to higher dimensional spaces. And we can replicate the same analysis where you have your loss function, and you can write your loss function in terms of this compact representation, where this x is the data metrics, where each row is a data point, or sample or observation, and each column is a feature or predictor. And therefore, this is of size n by d plus 1. And that's exactly how scikit-learn expects you to provide this input data. Now we have these vector of unknowns that we have to estimate them. And these are the ground truth outputs. And therefore, we have an optimization problem that we have to solve that we can use scikit-learn. As we said earlier, we can show that the gradient, which is the vector of all partial derivatives, has this very nice format Obviously, if you have no linear algebra, this is not too difficult to show in a general case, but we already have done this for the 2D case. And you can solve these using this closed form solution, which is known as the normal equation. But what we really want to do in this video is to understand how to implement this using scikit-learn, because this course mainly focuses on programming aspects. So make sure that you look at the documentation page, because that's where you find a lot of information about what input arguments you can provide for this class. Remember, this linear regression is a class, so you have to instantiate it to create an object. So you understand the parameters that you can provide, the attributes that this object will have, such as the coefficients, the intercept or the bias term. You can also, for example, find the rank of the data matrix X if you're familiar with that topic from linear algebra. So you get a lot of useful information. And also, if you look at here, you have these methods that we saw some of them before, like .fit, where you can fit, which means that you train your model and finds data. The predict method, where you can make predictions. And if you look at it, there are also other options too. So we don't really need the other options very much in this course, but it is always a good thing to look at them just in case when you need them. So going back, I just summarized this information here in terms of the differences between parameters, attributes, and methods. These are the three things, regardless of what you're using, whether it's linear regression or regression that you used for your homework before. You need to understand and read these important pieces of information. And for linear regression, the fit method, as we said, it expects the data matrix X, which is n samples by n features, meaning number of samples by the number of features. And number of features here is the number of variables or predictors that we have. And Y is the one that represents the target values or labels associated with the input data matrix. So in this case, we can print the shape of X and Y. So something here that we say, which is very important, is that even though you have one feature, this n features is one, make sure that actually that's reflected in the shape that you have here. Right now, based on what we see here, x.shape, NumPy assumes that this is a one-dimensional array with 27 elements. But what you really want to have is to see that x is a two-dimensional array with 27 rows and 1 columns to make sure that this matches this definition here. So in order to do that, you can always use x.reshape and put -1, which means that you don't want to calculate the number of rows, but you want to enforce to have 1 column. So in this case, if I run this, you will see that now I get something very similar to what's inside X, but now we have these 2 square brackets, which, this tells us that now we have a 2D array. We have 1 column and 27 rows. And if I use dot shape here, you can immediately see the difference. Now, this version of X, where you reshape it, is actually 27 by 1. And to make this again clear, if you don't want to use -1, you can use 27 and 1. And that's the same exact thing, but it is more helpful if you just use -1. So now let's revisit the GDP data. So in this case, from scikit-learn's linear model module, we're going to import linear regression, and then we're going to instantiate it. And then, as we said, you have to reshape this X to make sure this is a 2D array and provide both inputs and outputs and use that fit method. And after that, now you can look at these attributes, where the first one is the intercept, the second one is the coefficient. So you can see that here we get very similar values to what we had before, 3.7 for the intercept, and this number, which is in the order of 10 to the -5 for the coefficient. So something that you may say is that, well, why this coefficient is too small, right? This is not a good idea to have like this very, very small number compared to this number, which is a few orders of magnitude larger. So that's where you can use the idea of pre-processing. So if you remember, in one of the lectures, we created a version of this min-max scalar, where if you provide a bunch of numbers, it scales them so that they're always from 0 to 1. So we can do the same thing here actually. And for the data matrix X that we have, we can use this min-max scalar. So very similar to any other ways that we can use object-oriented programming. You first instantiate it and then use a suitable method here, fit transform, to transform this. And now we can repeat the same exact process to train a regression model. And you can see that now we have a much more, I would say, sensible result where we have intercept 5.5, and then the coefficient is 2.28. And just to show the difference here, we can look at this x min max to show that actually how it works. So you can see that before, when we look at x, I think we have a version here, you got these numbers that, they were like 26,000 something, 27,000, right? So they were extremely large. But now when we look at this x min max, because we use this min max scalar, they're all from 0 to 1. So you can see that the maximum is 1 and then the minimum is 0. So this is somewhat easier to work with because you don't have to deal with these large numbers. Okay, so now let's look at how this model performs. In this case, we are using the version that is scaled using that min-max scalar. And so this means that for your test data, you have to use the exact same thing. You have to reshape it and then transform it. And if I run this, so you can see that now the GDP, the scaled version, is from 0 to 1. As we said, that's our input. And this is our regression line. And as you can see, the intercept here is 5.5, and the coefficient is, the slope is 2.28. So we didn't really change the problem, but by just scaling the data, we find results that are more stable and easier to work with. So now once you train your model, in these cases that you have a 1D problem, you can visualize the regression line and see whether this is a good model or not. But in many cases, if you have like, a high dimensional problem, you cannot visualize anything more than a 3D problem, right? So we need to have quantifiable ways of measuring the performance of regression models. And in order to find the list of all evaluation metrics, you can go to this link. So as you can see from now on, I can point you towards like the relevant part of scikit-learn to read and understand what possible options we have. Obviously, we cannot cover all of them in this course, but you can see that, for example, for regression, we have a lot of metrics that you can use. So whenever you want to use one of these, you can further, go towards the user guide or documentation page and understand how this in this case evaluation metric is working. So one of the ways of measuring performance is using mean squared error, where we have these true and predicted values. That's why we're using hat for predicted, which is the average loss, and the loss is measured using the quadratic loss function. And so the value you get after calculating MSE is a squared unit of the output. For example, let's say if it's a physical quantity, this means that now the error is in the units of the error is squared of the original output. And therefore, one possible way of handling this problem is to look at the root mean squared error, or RMSE, where you take the square root of the MSE that we did before. So in this case, the error that you find has the same units as the original output. And as we said, in this case, the best possible score is 0 if you have perfect predictions. But in general, this is a non-negative quantity, and larger values show more disagreement between true and predicted values. So you want to reduce this mean squared error or root mean squared error as much as possible. And just to show you how this works, we here create like a true versus predicted list, and we feed this to this mean squared error. There is an option inside this, which is called a squared, which is by default set to be true to return mean squared error. But if you set that squared to be false, then you find the root mean squared error. So here you can actually calculate this by hand too to make sure that we get the same results, but this should work properly. Another thing which is very important to measure the performance of regression models is known as the coefficient of determination, also known as the R2 score. And that's the formula for R2 score. So it's 1 minus, and then we have this term here, where in the denominator, we subtract each true output by the mean of the true output. So this y bar is the mean or average of the true outputs. And in the numerator, we have the sum of the residuals, right? So yn minus y hat n, where y hat is the predicted value. So this metric is very helpful because if you have a perfect model, then these residuals, they're all zeros, which is in the denominator, inside is in the numerator of the second term, which means that then the coefficient of the determination is 1 minus 0 or 1. So that's the best possible score. In this case, higher scores are better. So it's kind of like opposite of MSE. And you can see that if these y hat ends, they're all equal to y bar, meaning that the predicted value is just simply the average of the output in your label data set, then you get 1 minus 1, which is 0. And this metric can actually be negative too, meaning that you can get a situation where this fraction that you have here is greater than 1, which means that the whole thing is less than 0. But ideally, you want to be as close as possible to 1 and not below 0, because then means that you have a much better solution where you can just predict the average of output for all your training data points as the prediction for any new data point, and that will give you R squared of 0. And this quantity, again, the numerator is very important because it also has a very specific name, which is called residual sum of squares, or RSS. So that's the one that measures the amount of variability that is left unexplained by your machine learning model. And remember, the best possible score is 1, and a number near 0 indicates that the model doesn't explain much of the variability in response, because in that case, you can simply just always make predictions by looking at this y bar, which is the average of the output in your label data set. And you can see that in this case, if you find R squared, because these two lists are somewhat close, you can see get something which is close to 1. So in this case, we have reasonable value for R squared. The last topic we want to talk about today is about polynomial regression. So as we said, the linear model that we have is a really good thing if you have a linear relationship between inputs and outputs, but definitely it does not work if we have nonlinear relationships. So one way to get around this is something known as polynomial regression, which is a very simple trick. So as we said, the prediction model here is the dot product between these unknown parameters and the vector that you have for your inputs. And one thing you can do is actually you can apply a transformation on your input data. So if you remember, we had this framework before where we talk about data transformations, where you have polynomial terms, meaning that if you just have one input x, which is a scalar, then you get 1x, x squared up to x to some degrees. And if you have higher order terms, like let's say x and y, or x1 and x2, then you get x1 squared, x2 squared, x1 times x2, etc. And in order to do this transformation is actually something that is built in scikit-learn inside the pre-processing module, which is called polynomial features. To just show you how this works, we can actually look at like a synthetic problem where we create this data matrix called X, right? And this X right now has 3 rows and 2 columns. So if you use these polynomial features, and this is a class, so you have to instantiate it, and we set the degree to be 2, so we want to look at degrees up to 2, and transform these data metrics that we have here. You can see that we get the original features, which is like 0 and 1. Let's right now look at the first row. Then we get 0 squared, 1 squared, and 0 times 1. So that's what we explain here. And the same thing for the second row. So you can see that we have 2 and 3 that we had before. Now we have 4 and 9, and then the multiplication of these two, which is 6. And the same thing for the last row. And here I put include bias to be false, but if you set that to be true, you also see that extra 1 that is here, right? So that's exactly consistent with what we have here. In general, you can set this include bias to be true, and you get this extra 1. And after that, you get your original features, which we have before, and then the higher order terms. So to see how this works, let's create a synthetic problem, where in this case, we have these X values, and we use this quadratic function to generate the data. So if we plot this data, you can see that that's how this training data looks like. And the goal is that can we find a nonlinear regression model using these polynomial features? So in order to do that, you need polynomial features that we just discussed. You also need to incorporate these polynomial features with or into linear regression. So in this case, we can use something called pipeline. And in the next slide, I'm going to talk more about pipeline and why it is so critical in data science and machine learning. And also, we're going to import linear regression. So pipeline is kind of like a glue. What it does, it says that we wanted to do two things. For any input, we want to first apply this polynomial transformation. And then on top of that, when we get these new higher order features, we want to apply linear regression. So although we are using linear regression, because before applying linear regression, we have these polynomial features, our model can indeed now be nonlinear. And we call this object now any name you want, for example, like pipe. And very similar to linear regression, now you can use .fit and then .predict. And if you follow here, the rest of the code here that we have for plotting, you can see that these are the data points that we had. And this is our regression curve that we have. So right now, this is not anymore just a linear model, and it can actually be a nonlinear curve, as you can see here. So what is exactly pipeline? So pipeline is extremely helpful because in many advanced data science and machine learning problems, you want to do multiple transformations, and you want to do this in a very efficient and compact way. So what you can do is that you can create this object, which includes this chain of transformations. And as we said, it can be more than one. And at the end, you put what scikit-learn calls an estimator, which is basically a regressor or classifier. So these transformers are like polynomial features. Min-max scalar are classes that implement both fit and transform methods. And estimators, as we said, are the ones that they learn from data, meaning that, in general, like classifiers or regressors, these are the ones that implement the fit and predict method. So that's why when we said pipe.predict, it knows that it has to call the predict method of the last part. So this is very a smart way of doing this sequential transformation of data and then applying an estimator. And the last part of this lecture, what we're going to do is we're going to look at the impact of the degree of polynomial on the predictions of your model. So in this case, we have this for loop. We go through 3 cases. And you can see here we are considering degrees 30, 2, and 1. So three values for the degree parameter. And then the width of the line that we want to plot and different colors. And in each case, we use the degree that we have from this for loop. And also in this case, we're going to add more transformations. We're going to add the standard scalar transformation, which is the one that makes sure that the inputs are centered at 0 with variance 1. We do the polynomial features and then linear regression. So that's the pipeline that we have to just show you that we can indeed have more than one transformation. So right now we have 2 transformations and 1 estimator. And if we follow the same path and do .fit and then .predict, you can see that we get this very interesting curve, right? Which explains 2 very important topics in machine learning. So you can see that in this case, because the data that we created, we actually are here using this side information that we know that it's coming from a degree 2 polynomial. The curve that we find for predicted values according to degree 2 matches this data set very well. But obviously, when we use a degree 1 polynomial, which is just a linear regression model, you can see that this model does not fit this data very well. And in fact, it has a lot of bias, meaning that it does not capture the variability in the data. So this is what we call it as underfitting, meaning that when the model is too simple to capture the underlying structure. But on the other hand, we have something else which is even more important, which is overfitting. When the model is too complex and it starts to capture not just the underlying trend, but also the noise present in the data. So you can see here, when we set the degree to 30 using this green curve, yeah, this curve is going through almost all the data points, but obviously has a lot of oscillations and abrupt changes, especially you can see in these areas at the beginning and at the end. And that's really bad because now if you have a test data point, which is around, let's say, 2.6 or 7 here, then you may end up with really, really bad predictions that are far from where, these data points are. And therefore, this is something always important to consider, that you have to use the train test approach that we said to make sure that the error on the test data is comparable with the training data. And if it's not, and in this case, the error on the testing data should be much greater than the training data, that's we call as overfitting, which means that the model does not generalize well. So that's something very important to consider when working with nonlinear models to make sure that the model generalizes well. So in this case, again, we have some interesting homework assignments working with a data set that is included inside scikit-learn known as diabetes. We want to here, train regression models and be able to evaluate the model. We also have another data set called empty cars data set. So in this case, we want to use horsepower and weight of the car to estimate MPG or mile per gallon. Also, we are working with California housing data sets. So this is a point that we can use these real data sets to extract knowledge and perform data analysis using machine learning methods. Thanks for watching.